In this video, we're going to cover some chapter 17 questions on acid-base equilibrium. So the first question, what is the molarity of the OH ions in 0.04 molar ammonia, which is NH3? And they give you the Kb for NH3, which is a weak base, at 1.8 times 10 to the negative fifth. All right, so whenever they ask about pH, about POH, or concentration of hydrogen, ammonium, or hydroxide, you have to do an ice chart because it's a weak electrolyte and we don't know the dissociation rate or the amount of dissociation, which we can use an ice chart for. So we want to add our NH3 to water. And the reaction will create NH4 plus hydroxide ion, right? And we're trying to figure out the concentration of the hydroxide. So we do an ice table. The initial concentration of ammonia is 0.04. Water we don't count because it's a pure liquid. And the products initially at time 0 have 0 molarity. The change is going to be minus X for the reactants and plus X for the products. Then we will write our equilibrium expression, 0.04 minus X. Then you're going to have a net change for the ammonium ion and the OH minus at X. So then your equilibrium expression will be X squared over 0.04 minus X equals 1.8 times 10 to the negative fifth for Kb. Now, in this case, the value of ammonium or of concentration is 10 to the negative 2. And the Kb is 10 to the negative fifth. So the question could be, are you allowed to approximate this X, this minus X as being small and negligible? It's on the cusp for this case. It's borderline. But what we're going to do is we're going to leave this equation here, and we're going to solve it both ways. So I'm first going to solve it with the approximation, just because I want to prove a point here and just show in a question that is kind of on the cusp, meaning off by 10 to the 10th to the third. I want to see, or I want to show you how much of a difference it makes. So we're going to get rid of that X. We're going to say it's negligible for now. We're going to multiply by 0.04, and we have X is going to equal the square root of 1.8 times 10 to the negative fifth times 0.04, which equals 8.49 times 10 to the negative fourth. So that's going to be X. Now, X corresponds to our hydroxide concentration. So that's going to be the answer for this question. So what is the molarity of the hydroxide ions? The answer is 8.49 times 10 to the negative fourth molarity. Now let's try to figure out X without the approximation. And we're going to solve for this X using a quadratic formula. So if we were to manipulate this equation to get the quadratic formula, we would end up with X squared minus 1.8 times 10 to the negative fifth X plus 0.04 times 1.8 times 10 to the negative fifth is going to equal 0. And we can solve for that as well. X equals 8.48 times 10 to the negative fifth, or 10 to negative fourth molar. So you can see both approximate and not approximate answers are very, very close to each other, almost identical. So for this case, we can do that. We can approximate. Now, another follow-up question they could ask is, what is the pH? Usually they ask pH-based questions. So what we can do is we can take the negative log of the OH concentration, which would give us the POH, which is 3.07. And then we can solve for the pH, which would be 14 minus 3.07 which is 10.93. So that's pretty basic. That makes sense because it's a weak base. Okay, moving on to the next one. When 0.0038 moles of a weak acid are dissolved in enough water to make 0.5 liters, the pH of the resulting solution is 6.01. Calculate Ka. So again, an ice chart is needed here, but it's from a different approach. We are given a solution of the weak acid and we're given its pH and we're asked to find Ka. So we kind of have to work backwards here. There's a lot of things we can do first, but first I would see that the pH equals 6.01. This means that the negative log of the hydrogen concentration equals 6.01, and we can solve for the hydrogen concentration. So initially where, let's say in the ice table we just did, we would be looking for X in order to find the pH. We can directly calculate X first, and then we can populate the ice chart later on. So we can put a negative over here, negative cancels out, take 10 to each side. So we were looking for the H concentration is equal to 10 to the negative 6.01. And that number is very small. It's going to be 9.77 times 10 to the negative 7th molarity. So that's what X is going to be. I'm going to put equals X. All right. So now we have other information. We have the initial concentration of the acid. And that's another thing that we always need when we do an ice table. So we're just going to put a general equation for the weak acid first. We'll do HA plus H2O yields H3O plus A minus, which is the normal dissociation of a weak acid. And we're going to write our ice table. And for the initial acid concentration, we have 0.0038 moles divided into 0.5 liters for our solution, which is going to be 0.0076 molar. So we can put that in here, 0.0076. We have nothing in this column, and we have 0 and 0. Then in this change, we're going to have minus X plus X plus X, and we have 0.0076 minus X. Now for H plus or H3O plus concentration, we have that number already. It's 9.77 times 10 to the negative 7th. And same thing for A, we have that number as well. So, and also we have the equilibrium concentration of HA, so because we have X. Now, with that information, we can solve for Ka. So we can use the equilibrium expression and do 9.77 times 10 to the negative 7th, which is the products here, which is the equilibrium concentration for both H3O plus and A minus. So we have those squared, divided by the acid concentration change, 0.0076 minus 9.77 times 10 to the negative 7th. Now, again, just like this equals Ka, just like we do for when we solve for X, this X is so small, the 9.77 times 10 to the negative 7, that it is negligible. It doesn't really matter much because we can easily put this entire expression in our calculator. But since the starting concentration of the acid is only 0.00, well, it's 10 to the negative third. Meanwhile, the X value is 10 to the negative 7th. So it's definitely negligible when you're adding and subtracting. So we can solve for Ka very easily. And it equals 1.26 times 10 to the negative 10th. So it's a very small Ka. It's a very weak acid. And that makes sense because the pH of this weak acid is 6.01. So it's barely an acid. So that makes sense that it's a small Ka. Moving on, third problem. We have calculate the percent ionization of that much phenol in a very dilute solution. So we need the Ka for phenol, which is 0.3 times 10 to the negative 10. Another extremely weak acid. And phenol is also known as carbolic acid. That's another word for it. And all it is a benzene ring with an OH group on the end. Okay, so now let's write an ice chart. So we're going to write just, instead of phenol, we'll just write HA. And we're going to add it to water. And we're going to create A minus plus H3O plus. And our ice chart, and as you can see, this is pretty repetitive. Our ice chart, we have our initial concentration, 5.82 times 10 to the negative 6th. We have 0, 0. Then we have minus X plus X plus X. 5.82 times 10 to the negative 6th minus X, X, and X. Our final expression, X squared divided by 5.82 times 10 to the negative 6th minus X equals 1.3 times 10 to the negative 10, which is the Ka. Now, because the Ka is extremely small, you might think, okay, definitely a question where we can approximate by getting rid of the minus X. You're right, but it's definitely important to make sure the concentration is much different. In this case, they're 10 to the 4th difference. That's enough. But let's say there's an extremely dilute acid that's even more dilute than this, and the concentration is 10 to the negative 9th. In that case, you won't be able to make X negligible. But in this case, it still is. So we can approximate, and we can multiply and take the square root. So we would end up with X equals a big square root of 1.3 times 10 to the negative 10 times 5.82 times 10 to the negative 6th, which equals 2.7 times 10 to the negative 8 molar. And that makes sense. Extremely small concentration for an extremely dilute, weak acid. So we are calculating the percent ionization. Now, percent ionization, what that means is the amount of ionization, obviously, which is either expressed by the A minus or the H3O plus, because they're usually in a 1-to-1 ratio. So whatever X is in this case, over the original concentration of the weak acid, which is 5.82, 10 to the negative 6th. So we're going to take our ionization level, which our H plus concentration, or H3O plus, is 2.7 times 10 to the negative 8. And we're going to divide it by 1.3 times 10 to the negative 10. So you can see this will maybe be a 1% or 2% ionization. The 2.7 times 10 to the negative 8 over, we would have the percent ionization, which would be H3O plus concentration, which we calculated as 2.7 times 10 to the negative 8, divided by the initial concentration of the acid, 5.82 times 10 to the negative 6. And this is somewhat in the single percentile range, maybe a little bit, maybe 0.5% if I had to guess. And we'll calculate that right now. And it is almost exactly 0.5%. We have 0.46% ionization. And also from this, you can calculate the pH by doing the negative log of the value for X, etc. All right, moving forward, we have when 1 gram of thiamine hydrochloride is dissolved in water and diluted to 10 mils, the pH is 4.5. The formula weight of the thiamine hydrochloride is 337.3 grams per mole. Calculate Ka. This is a very similar equation to what we just did. But was one more step required, a Chem 1 step, right? So instead of going directly from the moles and liters to molarity, we need to go from grams to moles using the molar mass and then to molarity. So let's do that first to get it out of the way. And then we can deal with the pH. So we have the thiamine hydrochloride is 1 gram. We know the molar mass is 337 grams per mole. And then once you divide the grams by the molar mass, the grams will cancel out and you get moles. And that answer is going to be very small. And it is 2.96 times 10 to the negative third moles. And we can divide that by the liters, which is 0.01. Which equals a molarity of 0.296 molar. Okay, so we have the initial concentration of the weak acid. Now we can find out the final concentration of the hydrogen or the hydronium H3O plus ion by using the pH. So again, we'll cut to the chase this time. 10 to the negative pH equals the concentration. So 10 to the negative 4.5 is going to equal 3.16 times 10 to the negative fifth molarity of H3O plus. All right, so now we can write our ice table and we have everything we need to know. So again, we're not going to write the entire formula out. We'll just do HA plus H2O yields A minus plus H3O plus. Here's our ice chart. And our initial concentration, 0.296. Water we don't do, and we have 0, 0. Minus X plus X plus X. And our X, in this case, we know as 3.16 times 10 to the negative fifth, both for the dissociated, the conjugate base, and the hydronium ion. And this we have 0.296 minus X. So since we have the value of X, our work is basically done. I'm not going to solve this one out because whatever, I'll be lazy, let you guys do it. But for Ka, our expression is going to equal 3.16 times 10 to the negative fifth squared, because you have your products, and that would be the conjugate base of the acid and the hydronium ion, divided by the concentration of the reactants, which is 0.296 minus X, which is 3.16 times 10 to the negative fifth. And in this case, again, you can use the approximation because the initial concentration of acid is 0.296 molar, while we don't know the Ka, but we do know that the amount of ionized acid is on the order of 10 to the negative fifth. So it's going to be very small. So we can use that approximation and we can solve for your answer, whatever that may be. For this question, we're asked to calculate the pH of sodium acetate. Now, sodium acetate, although it may seem like a normal salt, is actually basic. And the reason why is because if you put this into water, it will immediately dissociate into sodium and the acetate ion. Now, sodium, when it reacts with OH, makes sodium hydroxide, but then it breaks apart immediately because it's a strong base. So sodium is just going to float freely in solution and not really do anything to the pH at all. It won't, in other words, it won't quench the hydroxides from the solution. They will still be floating in solution with water. But acetate, on the other hand, when it forms its acid or base, in this case, acetic acid, it's a weak base. And this water, or this hydrogen, doesn't like to come off of the acetate too readily. And this means that you can think of the acetate as being able to strip hydrogen from the water in the aqueous solution, thus lowering the hydrogen concentration that is free in water and increasing the OH concentration that is free in water by stripping the H off of the water molecules, both at the same time, and both correspond to raising the pH or making the solution more basic. So what we can do is we can have an ice chart to show this behavior with a certain concentration. And using the Ka and ultimately figuring out the Kb for the sodium acetate, we can figure out the pH of the solution. So let's write the equation. C2H3O2 minus plus H2O yields HC2H3O2 plus OH minus. Now, the initial concentration of the sodium acetate is 0.02. And you notice how I didn't put sodium here. Sodium immediately dissociates, right? Sodium acetate is an extremely soluble compound. So the sodium goes off and does whatever sodium does, just sits in the solution. It doesn't matter. It doesn't correspond to the acidity or basicity at all. And then we have 0 here, and this is just like a normal ice chart. So 0.2 minus x, and then we have plus x, x, plus x, x. And we have the expression for equilibrium of x squared over 0.02 minus x. And this is going to equal not the Ka, but the Kb. The reason why it's Kb is because we have a basic equation in front of us. We're taking the acetate ion, it's stripping the hydrogen from the water to produce hydroxide ions in solution. So we're given the Ka for acetic acid. We can figure out the Kb by doing 10 to the negative 14 divided by the Ka to figure out the Kb, which is 5.6 times 10 to the negative 10. And we can make the equilibrium expression of this acetate ion base solution and make it equal to the Kb, which is 5.6 times 10 to the negative 10. Now, since this Kb is very small and the concentration is relatively large, 0.02 in comparison to 10 to the negative 10, we can then cancel out this x, and this x becomes negligible. So we can solve for x. It would be the square root of 0.02 times 5.6 times 10 to the negative 10. It looks like an 18. It's a 10. And this is going to equal times 10 to the negative 6th. Now, this x corresponds to the hydroxide ion concentration. So we can find the pOH by doing the negative log of that, which would be negative log of 3.3 times 10 to the negative 6th, which equals 5.48. And then the pH would be 14 minus 5.48. Which is 8.52. As you can see, that corresponds to a weak base. Moving on, we have calculate the pH of 0.0024 molar of barium hydroxide. Now, barium hydroxide is a group 2 hydroxide, making it a strong base. So what we can do is we can calculate immediately the concentration of OH, which the dissociation looks like this. Barium hydroxide yields Ba2 plus 2 of OH minus. Therefore, the concentration of OH is going to be 2 times the concentration of the barium hydroxide. So the concentration of OH minus is going to equal 0.0048 molar. Now, an important distinction is bases that have hydroxide on them are covalent. No, sorry. Bases that have hydroxides on them are ionic. That means they are strong electrolytes, most of them, and they will dissociate completely. Unlike acids, which a lot of them are covalent, and the first proton will only dissociate, such as where we see diprotic strong acids such as sulfuric acid, the first acid dissociation is going to happen 100%, but the one after that is considered to be a much, much weaker dissociation. In basic solutions, it's a bit different, where because you have an ionic compound, every one of the ions will dissociate. You'll have both hydroxides coming off of the barium at the same time because neither one of them takes preference. So that means the active hydroxide concentration in the solution will be simply equal to the amount of hydroxides there if it is a strong base. So there's no multi-dehydroxylation like there is for the deprotonation in different steps. It all happens at the same time for these strong bases. So what we can do is do the negative log of 0.04 or 0.0048 molar, and that will equal the POH. And just to save time, I'll do 14 minus POH equals pH, and you can solve that on your own. All right, the last one we'll do is state whether the following aqueous solutions are acidic, basic, or neutral. So let's figure this out. So CuCl2, so copper, and then Cl. The base version of copper is copper hydroxide. That means it's a weak base. For copper hydroxide, that's a weak base. That means if you put copper in the solution, what's going to happen to its pH? It will suck up most of the hydroxides from the water, and it will stay with the copper, thus taking them away from the solution, meaning this is going to be acidic. Meanwhile, chlorine, its acid form is HCl. That's a strong acid. So that won't form at all because hydrogen will just dissociate immediately and be deprotonated. So that won't have any effect on the pH. So for copper chloride, it's going to be, I'll put A for acidic. For sodium and phosphate, same approach. But for sodium, the base version of sodium is sodium hydroxide. That's a strong base. That's not going to have any effect on the pH because the sodium will completely dissociate from the hydroxide, and it will not permanently capture, if you will, one of the hydroxide ions. Phosphate, on the other hand, it will capture three hydrogen ions because it's a triprotic acid. And all three of those hydrogens, meaning the H3PO4, H2PO4, and HPO4, are all weak acids. So what that means is phosphate does a very good job at stripping the water of its hydrogen, meaning there are less free hydrogens in solution and there's more hydroxides in solution. So the ratio gets thrown off balance in favor of hydroxides, meaning that Na3PO4 is a base. Next one. So in this case, NH4Br, the acid form of Br is a strong acid, meaning it's not going to be able to quench the hydrogens from the water, so nothing's going to happen there. And ammonium hydroxide is a weak base. Therefore, it will take in the hydroxides, making the solution more acidic, leaving more free hydrogen in solution. So C is acidic. Magnesium sulfide, Mg and S. Magnesium, it creates a strong base with hydroxide. Therefore, nothing's really going to change the pH at all because the magnesium doesn't have a strong enough connection to hydroxide to rip it from the water and keep it stuck on. Meanwhile, sulfur, just like we saw before, can be a diprotic weak acid, meaning it can take a lot of hydrogens, 2 hydrogens each, 2 hydrogens per sulfur, from the solution and strip the water of it, thus creating more hydroxide ions that are free in solution and less hydrogen ions free in solution. So this would be another base. And that's it for this video. If you have any questions, please leave a comment below and be sure to like and subscribe to the channel. Thank you.